All right, time for the last problem for the part 2 problem. All right, so this is part D. It wants us to calculate the final speed using energy and work. All right, so let's start with what we know. We know that there is obviously a potential energy, and potential energy in a perfect system is always equal to the kinetic energy. But we have two forms of kinetic energy because our object is rotating. It's not like a block sliding down, right? So we have kinetic energy, which is the rotational kinetic energy, and then we have just your standard kinetic energy because the object is moving down the ramp, right? And so we can input all of the equations for these. So we know that potential energy is equal to mass times gravity times height, mgh. Then you have rotational energy, kinetic energy, which is equal to 1/2 I omega squared. And then you have, oops, look at that R in there. Then you have your standard straight line kinematic kinetic energy, which is 1/2 mass times velocity squared. All right, so now we'll input these values here. This problem is definitely a lot easier than the last one because it only takes about one step instead of three. So we have mass times gravity times height is equal to 1/2 inertia times omega, which is the angular velocity, plus 1/2 mass times velocity. Okay, so we're finding the final speed again. So we need to isolate velocity here. And we have a lot of these values. We have the mass. We know what gravity is. We have the height. We don't have the exact value of inertia, but we have an equation. And we don't have the angular velocity, but we can convert these. We know how to convert these. We got some tools in our tool belt that can help us with that. So we know from the beginning of the problem, inertia is equal to, let me make sure I get this right here. I believe it's 3/5. Yes, no, 2/5. Glad I checked that. So 2/3 mass times the radius squared, right? So we're going to sub this guy into there, but then we still have omega, but we know omega is equal to velocity over r, right? We're converting the angular velocity to straight line velocity, so velocity over r. So we can sub these values in, and that's going to make it a lot easier for us, right? So we have mass times gravity times height is equal to 1/2. We're going to plug the inertia in. Let's see, 2/3. We'll put this into parentheses to make it a little bit easier to understand. Mass times the rotation, or sorry, the radius squared. All right. That's the little I here. And then we're going to sub in omega, which is squared. So velocity, we'll wait to do that actually. We'll do r, we'll do this squared. This is going to just distribute in, so we have velocity squared, radius squared, but I'll do it this way to help. And oh, we're running out of room. Oh no. 1/2 mass times velocity squared. All right. This makes it a lot easier for us, right? Because we have all of these values. We have mass, we have gravity, we have height, we have all of this except for velocity. So from here, it's just straight algebra. All you have to do is manipulate the variables. Super simple, okay? I'll do a little bit. I might skip around, but I'll follow along. Let's see, 1/2. Let's see, multiply this. That's going to be 6/2, right? 2/3, 1/2, 6/2. Then we'll have mass, and this square is going to distribute into the radius squared, and these are going to cancel out. So we're going to be left with velocity squared, all right, plus 1/2 mass times velocity squared, all right. And so from here, you'll notice we have a mass on every side of the equation. So we're going to divide by the mass. That's going to give us gravity times height is equal to 2/6. We can actually simplify that more. I'll do that in a second. Velocity squared plus 1/2 velocity squared. All right. So now we'll add together 2/6 and 1/2. We'll do it on my calculator to make this video fast and simple. 2/6 plus 1/2 is going to give us 5/6. All right, so we got gravity, height equals 5/6 velocity squared. Then we're going to move that over and then square root everything. So that will put us at 6/5 gravity, height, root that equals velocity. And then we already have gravity and height. We know those. So in this problem, the height is 1.2. So let's see. We'll do root 6/5 times 9.8. Oops, putting that in the denominator. Don't want to do that. Times 9.8 times the height, which is 1.25. That's going to give us 3.83, which, if you remember from our last problem, is the same velocity we got. So 3.83 meters a second. And that is how you solve this problem with both the energy equations and the net torque and net force equations. Thanks for watching.